notices out of the way, I'm going to first of all introduce some of the topics, and it may seem strange that I introduce it in the context of aquatic geochemistry, but really the type of chemical principles that I will be dealing with really come out of a discipline that crosses the boundaries between soil chemistry and aquatic chemistry, but most of the formal theory that's come out of it has actually come out of aquatic chemistry, so where people are interested in the interactions between water and sediments, which is ultimately pretty much what goes on in a soil. So never mind the nomenclature here, we'll get to a place where we need to be and revise the type of principles that we need to get us ahead with some of the other stuff that we need to do. So I won't spend too long introducing that. So really, I will argue that we are interested in the types of chemical reactions that control the composition of water. Now, in the context of soil science, this is the pore water in the soil, and I will, as we go, it's quite a long argument to get there, but let's just assume for now that the water in the soil, so the water that exists in equilibrium with the solids, is really the essential part of the system when we think about issues like bioavailability and mobility. So there's a theory, which I'll develop a little bit later on, called the free ion activity model, which says that any organism that's living in the soil, like a plant or microbes or whatever, only really has access to the ions that are dissolved in the pore water in the soil, right? And all the other stuff, which we'll get into today, is inaccessible for one reason or another, either physically or chemically constrained. It's locked up in the structure of minerals, or it's in tiny little pore spaces that are inaccessible to roots or microbes. So what we really need to deal with then, if we're trying to understand the biological function of soils or issues like mobility of elements, we need to understand that balance between the solids and the solution, or really what is controlling the composition of the solution or the pore water in soils. So there's a whole lot of disciplines, obviously, that need to understand the concepts that inform us about that particular question, what controls water composition, and we're interested in the soil side of it. Okay, so what we try to understand then is what the not only just the concentration of elements are in that pore water, because that's not enough, as we'll see. That's insufficient to explain some of the phenomena that we see. We also need to go as far as chemical species, and that's why for you guys it'll be tomorrow morning, we will go through a fairly detailed geochemical modelling exercise. We'll use some real data, water composition from Robertson Park, and we'll use that to try and deduce some of the reactions that are controlling the composition of that water, and that's where we use this program called Freaksy, which does sound like a bit of a hip-hop group or song or something like that. Not, I'm too old to know about that sort of music, but it is a very, very powerful program for estimating composition of solutions and also using the types of reactions that occur within soils to make that prediction. All right, so we're going to do that. We're going to actually calculate some of those things that are conceptually important. Now, of course, there's a whole bunch of context. I think I've already unpacked some of that enough. What we do need to know is that in real life we have a system which is probably way too complex to provide a model of that completely represents the system. And the reason for that is that something as on the face of it, as simple as a soil, contains a whole lot of stuff. First of all, it's multi-phase, so we need to consider both the solid, liquid and gas phase in soils, and we'll unpack some of that with you today. Come in. But that, not only that, there are living things in it. Living things, from my point of view as a chemist / geochemist, occasionally dabbles in living things. There are sometimes unwanted complication. Plants and microbes and things, although I collaborate quite a lot with plant people and microbe people, they're not as nice and tidy as chemistry. So the biota for me is messy, and what it does is tends to make predictions messy and so on. So the presence of biota in the system makes it chemically much more complex than I would like it to be, but we can't ignore it, obviously, and so we simplify things a little bit, and as we go on, we'll find out what some of those simplifications are. Remember that we also, in a soil, have an open system, right? So we also need to consider what's happening outside the system, and we'll deal with some of that tomorrow morning in terms of openness to the atmosphere and things like that. Basically treating the atmosphere as an infinite sink of things like important gases like carbon dioxide, which are controlling some of the properties of the system. So we've got stuff coming in, stuff going out all the time. That's difficult to simulate, and we won't do a dynamic simulation in our practical class, just partly because we don't have time, and it's a very, very complex thing to do. So we will consider a system at equilibrium and have a fairly static simulation, but you'll find out that can get pretty complex on its own, right? But in the real world, we've got stuff changing all the time, matter and energy coming in, so material coming in, but also things like temperature changes occurring and so on. And also that, again, as we'll find out when we just look at the chemistry, if you change one thing, there's a cascade effect. It affects a whole lot of other things. So if we change the position of one equilibrium or the concentration of one species in the system, the prime example of that would be the concentration of hydrogen ions. We change pH, it changes a whole bunch of other reactions and can change the whole behaviour of the system. Another thing is that we need to consider reaction rates. Now hopefully we'll get to that today, but in 3 hours we may be pushing it. Okay, now the bottom line of this is that although we use chemical equilibrium principles, and don't worry, I'll explain what all that means as we go, we probably don't reach a true chemical equilibrium. Now what that means is that the numbers that we typically use to characterise chemical reactions, equilibrium constants or solubility products and things, maybe in soils we're pushing that envelope a little bit and they don't really apply that much because of the dynamic nature of the system. Things are changing all the time. So we probably have systems at what we call steady state, where we have a dynamic system where change occurs all the time, but it's a balanced kind of change. So inputs match outputs so that the system is relatively stable. And in the long term, that's probably true, although in the very, very long term, it's not true at all. So we need to consider timescales. In the real world, again, we won't do that. Okay, so just a few justifications of why we're here. Why do we consider soil geochemistry? Well, there are some key Earth system processes that are controlled. For example, the availability of certain elements to plants and other biota that live or depend on the soil system is to a large extent controlled by the chemical reaction. So we kind of need to understand that. But also in terms of mobility, and for most of us who may be not coming from a geological perspective, the dispersion and stuff from ore bodies is less important perhaps than, for example, dispersion of pollutants. So the mobility of things like metals and organics and so on is controlled, again, to a large extent by chemical reactions, particularly for things like metals, which is my area of expertise, as you'll find out, because I'll talk mostly about that and talk very little about organics and things. And we can, but we can have some discussions on those if we need to. And also, I guess, issues of development of the soil ecosystem, so the release of things during the weathering process as soils form, the behaviour of those elements that are released and what they do in soils, whether they form another mineral phase or are completely lost from the system, depends again on chemical processes. So what we should do is have a look at some of these. Now, go through some of the history of it. This probably isn't bona fide history, but I found it on the internet, so it must be true. In fact, this really covers a little bit more what we're going to address. So, although I think the context is slightly stretched here, the point that the shooter is making is quite valid, I think. In fact, they both make a valid point in that some forms of elements are not bioavailable, right? So, of course, the the lethality of a bullet is probably not really due to its chemical form, but you kind of get the idea, right? That the chemical form makes a difference. So I'm going to start here and look at a plot of groundwater composition. Now, why do we start here? Well, first of all, this illustrates some interesting points. First of all, let's put it in context. What is groundwater if it's not just water in contact with some mineral phases? So it's something that resembles the poor water that might exist in soils. Okay, so let's assume that that's what we're looking at here. And what we've got is a plot of really a cumulative frequency distribution of concentrations of different elements in a whole range of water samples. And so this is done by the USGS in groundwater. There are tens of thousands of analyses for major elements, fewer for trace elements because they're harder to do, but they represent a very, very large sample, maybe even approximating a population of things. And we see some interesting features of these data. So I'm going to just focus on a couple of elements. First of all, here's something we need to remember. Different elements behave differently, all right? So the concentrations of iron, for example, that we see in groundwater, or for groundwater read the pore water in soils, certainly is quite variable, and that's one of the features of the data. So we see iron concentrations in these data anyway, going from about 0.01 milligrams per litre, or 10 parts per billion, up to about let's say 50 milligrams per litre. So there's several orders of magnitude change, and you could ask the question, why? What's different about this groundwater here that the concentrations of iron are so low compared with this groundwater over here where the concentrations of iron were really high? Okay, so hopefully we're going to get some sort of handle on what might control absolute concentrations. That's one interesting thing. Here's another interesting thing, that iron behaves quite differently from something like chloride. Right? Some of you may know a bit about the different chemistry of these elements in the environment. So we know, just to a fairly large extent, the concentration of chloride probably doesn't reflect the chemistry of the system at all, because chloride is what we call a conservative element. It doesn't interact significantly with its substrate. It doesn't adsorb. Its compounds, by and large, are pretty soluble, and so the concentrations of chloride are probably much easier to explain than the different concentrations of iron. So whereas for iron we need to understand a whole raft of chemical reaction types, including oxidation and reduction, formation of solids, that's precipitation, or the reverse, dissolution of those, and we also need to understand the interaction of the iron with pre-existing solids in the system. So a type of reaction that I would call adsorption of some types, and go through those today. We don't have to consider those types of reactions for chloride to a first approximation. So chloride concentrations probably represent pretty much dilution of chloride-rich waters like seawater or rainwater, which brings seawater onto land. All right, so there are some differences, and of course you can apply similar ideas to every element across the periodic table. So again, we're seeing lower concentrations for other elements, but again, large ranges across at least 2 orders of magnitude, so 100-fold to maybe 1,000-fold difference in concentration, depending on where we are, depending on where the sample is taken. All right. So why is that? Well, hopefully we'll go along and have a look. So just to remind you where stuff comes from initially. So ultimately, we're dealing with the Earth's surface, so we need to think geochemically of the composition of the crust, right? Because that's where everything started from in the first place. The rocks in the crust contain, well, we know they contain mainly oxygen and silicon and aluminium and iron, and that's where those elements come from. They also contain most of the periodic table. And so when they break down, they release material, and in soils we find all of these things. We find residual material which doesn't change that much, so minerals like quartz and some of the more what we call recalcitrant phases like zircons and titanium oxides and things. They just don't break down during weathering very quickly. They do eventually, not very fast. In soils mostly, we'll have a mixture of that type of stuff and what we call the weathering products, the solid materials that form during soil formation. Now we're going to come back to some of these in a minute, so just store them away in at least the medium-term memory for a while. So we have iron oxides and the phyllosilicate minerals like kaolinite and smectites and a whole bunch of other clays, aluminium oxides and things. They're all really important. And I would also include in here weathering products of living material, so organic carbon, the humic materials that end up in soils. From a simple or simplistic chemist point of view, they're just the weathering products of life. We'll include those in our mix later on. Of course, we have soluble ions. Now, these are the materials which are either lost from the system because they're mobile, or they can contribute to biological systems because they're now in the pore water. So weathering, in particular chemical weathering, creates a diversity of material, and it's the interactions really between the soluble ions and these weathering products, including organic matter, that I think we need to consider as we go on. Now, there's a bit more information on that slide, so we're going to focus on that part of the system there. All right. So in terms of an aquatic geochemical process, there's a whole bunch of things that can go on. I've mentioned some of them already. Even we've got to include life in there somewhere, and the main function of life from a soil chemistry point of view is to put carbon in soils, so we'll leave it at that. Things photosynthesize, they die, they put carbon in soils, end of story, right? That's life summed up, give or take. Even we end up there. The net contribution of humans to soil organic carbon worldwide is probably quite small. So I'm going to go through each of these blow by blow, and hopefully by the time we get to about 11:15, we'll understand or remember soil chemistry so well we can progress. All right, so we'll focus first of all on this one here. Okay, so the atmosphere is highest in altitude, so we'll deal with it first. Gas exchange with the atmosphere is something that we need to consider because, for a couple of reasons. There are two main gases that I would say that are probably the most important that we need to consider. Oxygen, because the availability of oxygen in soils determines whether it's an oxidizing or reducing environment, right? And so the absence of oxygen, such as we actually saw a bit of this out at particularly those of you who wandered down and saw what Falco was doing with his sediments, creates very reducing conditions. So the grey and black smelly materials that Falco was pulling out from depth along the shoreline there existed because of an absence of oxygen. So we need to understand a little bit about what's going on there. The other major gas in the atmosphere that we need to consider, the rest of it's nitrogen. Nitrogen, from a chemical point of view, doesn't do a whole lot. It's kind of important for plants, but we've already dismissed them summarily, so we won't deal with that anymore. Carbon dioxide, though, is important because we know that carbonate minerals are important, right? And gases also dissolve in water, in particular carbon dioxide dissolves in water to give carbonic acid, and subsequently a whole range of carbonate species, and we'll talk about these when we do the prac with you tomorrow morning. But it has a very important function, not only in providing an anion for things to form solids with carbonate minerals, but also in controlling pH. So a lot of natural waters are actually buffered by the carbonate-bicarbonate acid-base system. All right. So we need to understand what controls gas dissolution, and we will include gas dissolution at least implicitly in our model. So we usually consider that gases reach equilibrium, although that may be slow in some systems, right? So some waters are stratified in lakes and things, but and in soils we can have diffusion significantly limited, but we will talk about that in another context, particularly in the context of oxygen diffusion. Right, so if things do come to a stable equilibrium, if the reaction goes to completion basically, here's how we understand gas exchange with the atmosphere. So the gases enter the system and they dissolve in the water, and there's a law, if you like, or an equation by which we can calculate the concentration of gas in the water. So AQ meaning aqueous, or in water, is simply the partial pressure of the gas multiplied by some magic number, and that magic number is called the Henry's law constant, and they're tabulated. Somebody decades ago went and measured a whole bunch of Henry's law constants for a whole bunch of gases at a range of temperatures and pressures. So if we know temperature and pressure, and usually we assume that pressure is, you know, standard atmospheric pressure, temperature pretty easy to measure, and we know something about the partial pressure of the gas. That's the fractional amount basically of that gas in the atmosphere. So for example, carbon dioxide just hit 400 ppm a little while ago, sadly. When I was at uni, still showing my age, we used to say that the concentration of carbon dioxide in the atmosphere was about 280 to 300 parts per million. It's going up, all right? So, but anyway, so just to prove that you can find Henry's law constants for things, here's a bunch of them. They're different for different gases, and they are dependent on pressure and temperature. So these will be for standard conditions. In chemistry, standard conditions are usually 298 Kelvin, which is 25 degrees C, and 1 atmosphere pressure. So not higher or lower than normal atmospheric pressure. All right, so that's pretty straightforward. We've got a theory to understand the dissolution of gases and water. Well, why is that important? It's important because dissolution of gases and water controls, in some ways, the chemistry of the system. We'll spend a bit of time looking at redox reactions at some later stage, but here's an example of our acid-base equilibrium of carbonate. Now, doesn't immediately involve a gas, but we'll get to that. Okay, so this is another type of reaction that we need to consider, and this occurs for a very wide range of materials in soils and sediments and natural systems, not just simple ions like carbonate. These types of reactions also occur on solids and things, so we need to understand roughly what an acid-base reaction is. So just hopefully this is revision for some of you. An acid-base reaction is when something can react with water to either pull a hydrogen ion off water or add a hydrogen ion into the water. So an acid adds hydrogen ions, a base basically reacts with a hydrogen ion from water and leaves behind something like hydroxide to make it more alkaline. All right, and there's a whole lot of theory. Now you don't. There's no need to copy down all this because we'll rely on Frigsy to calculate all this stuff for us. But the position of equilibrium, the degree to which that acid dissociates or forms hydrogen ions and the associated anion or conjugate base, is controlled by another number, right? And that number is called the equilibrium constant. It's related to the energetics of the reaction. So all the reactions, as you'd expect, are different. They have a different acid dissociation constant, which is effectively another equilibrium constant. And it's defined in this way: the concentration of the products of reaction, that's hydrogen ions and the conjugate base, divided by the starting point, the reactants of that reaction. And that's the conventional way, right, of defining an equilibrium constant. And again, these have been measured for many, many different acids: carbonic acid, phosphoric acid, sulfuric acid, organic acids of many different types. There are volumes and volumes of measurements of these, and we know what they are. We can look them up, and if we know them, we can use that information to start to make predictions about our system, and that's what we'll do tomorrow. All right, so the reverse reaction can be important as well. So complexation reactions, I mentioned those as well. This is something that we need to consider, and something that, again, we will include explicitly in our modelling exercise tomorrow. Particularly important for metals. So let's start to wander towards the chemistry of metals in soils. If we have a metal ion, for example, the one I've chosen here is cadmium, a divalent metal ion. It doesn't really matter which one we choose. It could be copper or zinc or gold even. Many of these ions can form what we call a complex, an association with another substance, often organic but not always. It can be something like chloride or sulfate or even hydroxide in solution. What it does is creates another chemical form, and so effectively enhances the concentration in solution, because we are able to have just the uncomplexed ion and a whole range of complex species forming in the solution. Now, the reason why that's important, we'll see in the context of its effect on other reactions later on. Okay, so complex formation is another example of an equilibrium reaction. We have a central ion and we form a coordination complex with one or more ions or molecules, which we give a special name to them. They're called ligands, and that's a chemical. Whoops, gone too far. Right, so we can form complexes of metal ions with chloride. So, for example, in seawater or saline groundwaters, a lot of our trace elements will actually be present as chloride complexes, right? And that means that the concentration in that water can be a bit higher than we would expect it to be on the basis of, say, solubility of the minerals of those elements, because of the existence of these species. So a whole lot of things can form complexes, and these are just a few of them. Fluoride as well is important, even bicarbonate, things like that. And we have quite an extensive formal nomenclature for complex formation. Basically, if you unpick this, and I don't suggest that you do now, you can do it at your leisure or self-punishment at some later stage. The way of expressing complexation equilibrium constants is just exactly the same as we do always, but I've just been very fussy about stoichiometry there, meaning the mole ratios and the subscripts and superscripts and stuff. So let's not worry too much about that. At the moment, just it needs to be considered that as a type of reaction, that in order to make a more realistic simulation of a chemical system like a soil, we would need to include that type of reaction. And the next one would be reduction or oxidation. So a whole lot of elements in nature can exist in more than one oxidation state. Now, oxidation reduction reactions are curious beasts. In chemistry textbooks, it's all expressed in terms of transfer of electrons. Now, what the heck does that mean? Obviously, electrons. So we'll bear that in mind, because we need to kind of consider that. And effectively what it means is that an element can exist in different oxidation states, and in our natural systems that we are considering, this depends incredibly strongly on the availability of oxygen in the system, or the concentration of oxygen in the system. Now, the concentrations of oxygen in natural systems has one major control, and that is biology, right? That's the primary control, and that's because in natural systems, respiration is going on all the time. And in the presence of sufficient oxygen, that respiration will always be a process that we call aerobic respiration. So microorganisms and other, roots do this as well. In order to supply themselves with energy, they will metabolize carbon compounds, right? That's what bacteria and fungi do. They decompose carbon. In order to do that, they use oxygen. Basically, they're burning carbon, biochemically. Now, in a soil, that process, unless oxygen can diffuse back into the soil, that process will consume the oxygen quite quickly. We've got reduced pore space inside a soil. There's not a lot of oxygen in there. It's about 20% in the above ground atmosphere, and it may drop considerably below that. And that can significantly deplete oxygen in a system unless the oxygen can diffuse easily back in. It can in a well-structured aerobic soil. But in other soils, if the pores are filled with water, we can decrease that diffusion rate by up to 4 orders of magnitude, about 10,000 times in a saturated soil. And so in many situations, we've got redox gradients. Right, so here's a couple of examples of redox transformations that we can have. Nitrogen exists in, I guess, simplistically in two main redox forms. In the presence of sufficient oxygen, it will exist in the most oxidized form, nitrate, but in reduced systems, it exists as the most reduced form, ammonium. And there are a number of intermediate, I guess, halfway points in between. Here's another reaction. I'll highlight this one just to, and we will come back to this hopefully, but in the absence of oxygen, some organisms can still process carbon. They can still decompose carbon. And the way they do that is they use something other than oxygen to oxidize things. Now, it sounds a bit weird, but there are a number of different materials or compounds or ions in soils that can act as what we call a terminal electron acceptor or an oxidizing agent, not just oxygen. So in some bacteria can process microbial organic carbon like this. So organic carbon gets oxidized through the normal oxidation products of carbon dioxide and water using sulfate as an oxidizing agent. These are called sulfate reducing bacteria. Very, very common in wetlands and things, and in marine sediments and in soils if we have wet enough soils. But they're only competitive with the other microbial population in the absence of oxygen. Otherwise, the other bacteria are too greedy. They're just using oxygen to plough through the organic carbon. Right. Now, how do we control this? So remember that we've got electron transfer involved. And the element, it's not a universal property of every element that they can exist in two or more stable oxidation states. There are a few that are important. Certainly carbon, the whole metabolism and biochemistry of life is based on the redox reactions of carbon. So we can't really ignore that, really. Nitrogen as well. Geochemically, the very, very important ones would be sulfur and iron. So sulfur can transition between sulfate in oxidized systems through to sulfide in reduced systems, and that's a very, very important reaction in some soils. Similarly, iron has two stable oxidation states, iron 3, which has very, very insoluble minerals and is strongly hydrolyzing in water, so it's quite reactive compared with iron 2, which behaves a little bit more like something like calcium. It's much less reactive, its compounds are much more soluble, and therefore it's more bioavailable and mobile because of that. So we haven't revised the stuff related to solubility yet, but we'll get there. So remember the importance of microbial mediation and oxygen diffusion in controlling redox reactions if we don't get to the rest of that today. And so a program like Freaksy will include these electrochemical principles. So it'll basically internally estimate what the activity of electrons is in the system and use that to calculate the position of equilibrium for reactions like ammonium oxidation or sulfate reduction. So we just need to know to include those types of reactions in a simulation if we're to understand a system well. Okay, so precipitation dissolution. Again, a very simple example. Calcium can combine with carbonate ions. If they're both in solution and the concentrations are high enough, we will precipitate a solid, calcium carbonate. The same principles apply for precipitation of anything, really. Iron oxides, even clay minerals, given the right conditions. And so they're an equilibrium process because the solid can dissolve as well. And so we usually consider precipitation and dissolution as a dynamic process where the rate of solid formation equals the rate of dissolution at equilibrium. And so we can use equilibrium principles to understand this as well. Okay, and the equilibrium constant is, again, it's given a special name for this type of reaction called the solubility product. And usually we consider the activity or the concentration of the solid. We can neglect that because we assume that it's equal to 1. Now that's an assumption that we can't always make with integrity for natural systems because it depends on the solid being pure and it having exactly the structure that we think it has. That is almost never the case, but we make the assumption anyway. It's too hard not to. Okay, so the solubility product is basically some critical product of the concentration of these component ions, which if it's exceeded, that solid will precipitate. If these ions are present at lower concentrations, they'll stay in solution, nothing will happen. But we exceed this threshold value, and in theory, according to chemical equilibrium, a solid will precipitate. And we can apply that to any solid. Okay? iron oxides, quartz, clay minerals, anything you like, sulfides, but here's a little warning. The reactions are usually pretty slow, so if we're trying to simulate a natural system and we include in our simulation a reaction where we're forming a very complex, highly crystalline solid, we're probably wrong, because that's the formation kinetics of that type of material are just too slow. So what we generally do, particularly in the short term, is to cheat a little bit and use our other chemical knowledge that simple, less crystalline solids are the ones which are more likely to form. So precipitation and dissolution, which is what we're going to focus on in the simulation exercise, is something which often doesn't actually attain a true equilibrium, particularly in dynamic systems. And we can have oversaturation, where the concentrations of these ions actually exceed the threshold, but still nothing happens, or undersaturation, where we have a solid present, but it's not dissolving, even though the concentrations of its component ions are actually low enough to allow it to dissolve. So both of those non-equilibrium situations can be present. All right, what other things do we need to consider? Whoops, okay, there we go. Lost my reactions there for a minute. As I said, we need to consider photosynthesis. We don't usually consider it as a separate process. We just assume that the organic matter, if we include it in our conceptual model of how a system behaves, has got there by photosynthesis, and we leave it there. We need not really information on how a material like that forms, but actually what its chemical properties are much more important. Can the organic matter, for example, form a complex with metal ions, or can it be an adsorbent for different materials in the system? And so if we know something about all these reaction types, we can then make judgments on whether biological uptake is likely, or whether we'd have mobility in the form of leaching or transfer to groundwater being likely processes. And so that would be I guess the hoped for outcome of a chemical, building up a chemical understanding of a system like a soil, that we could then use that information to try and deduce what other types of processes were likely. All right, we're going to carry on with this. I'm going to go probably for another 7 minutes, and then we'll break and we'll see how far we get with it afterwards. All right, so more revision. Any questions about that so far? Okay.
Actually,
Yeah.
I was going to ask you later on, but that graph that you put up with the cumulative, with those curves on it, I really don't understand what I'm looking at there.
Okay. Well, let's go back to that then, because that's, I guess it's useful, but it's not necessarily central to what we're doing, but it is useful. So what we're looking at there is basically data from analysis of a whole raft of groundwater samples, about up to 18,000 groundwater samples. And what it's showing is that so this is the cumulative frequency. So it's saying that let's highlight the iron line. Look at that. So here's a concentration of 10 micrograms per litre of iron, and they're saying that say about 10% of samples have concentrations of 10 micrograms per litre or below.
So
and then if you
the
go up,
percentage means you can always get a curve with any.
Yes, and by the time you get to 10,000 micrograms per litre, or about 10, say 50 ppm, all of the samples are in that range, right? And you can calculate a probability, I guess, for any, so 100 parts per billion. You've got about 50% of your samples below that particular concentration. Okay, that makes sense. Okay, good. Right, let's go back to any other questions. I think that's useful if there's questions like that. No such thing as a dumb question. All right. Okay, so we'll move on just quickly. I'm taking a little bit longer than I anticipated, but I think we need to get some of the basics. Otherwise, we won't necessarily have everybody on the same page tomorrow. All right. So I'm just going to quickly flick through the types of reactions that we consider in soil systems. First of all, chemical weathering. So this is basically the breakdown of primary rock-forming minerals into the types of things that we would more likely find in soils. Now obviously it's not a complete process. Some of the unweathered material still remains in a soil. So in the soils that we looked at in Banks Reserve, for example, we had primary minerals still present there, quartz, and probably a bit of residual calcite from the marine or estuarine influence on that environment. But we did have some secondary minerals as well. So the soils were not pure white quartz colour, they contained a bit of iron oxide in them, and that's a secondary mineral from the weathering process. And the general way that a weathering process occurs is from a primary mineral, it will react with basically the acidity present in water, natural water, from dissolution of atmospheric carbon dioxide, right? That's how a lot of silicate and other weathering occurs, is that we've got this slightly acidic water from dissolution of carbon dioxide in the atmosphere, and that slowly but steadily can dissolve the rock-forming minerals and release some soluble material. So in the case of a sodium feldspar, we would release sodium and bicarbonate from that process. The bicarbonate comes from the water itself. A bit of soluble silica gets released from the system, and some of the soluble silica and aluminium reforms, it precipitates another solid, right? So it's kind of an incongruent dissolution reaction where we're not dissolving the whole thing, we're dissolving some of it forms a new solid. That's a typical chemical weathering reaction. And so in the environment at Robertson Park, that the iron would have come from somewhere. So in the parent sediment or rock which formed the kind of sandy material, which is basically old dunal material which is blown up, there would have been some mineral which contained a bit of iron, so some biotite or hematite or something from primary rocks, and that would have weathered to form the iron oxide, the goethite, and other minerals that we find in those environments. All right, so weathering produces a whole lot of soluble material, but we retain some different types of minerals. Now those minerals are highly important in determining the chemical properties of the soils that we find. I've got a kind of busy slide here at the minute. So just to remind you that the phyllosilicate minerals, and we produced one here, kaolinite, during that weathering reaction here. Should bump this up, this is why I'm getting weird looking slides. They're basically silicon aluminium oxides, simplistically, but they have a very nifty structure. They've got these repeating tetrahedra of silicon and oxygen, and latched onto that in a kind of separate two-dimensional layer is aluminium with an octahedral arrangement, so a six-cornered figure of oxygen or hydroxide around that. Now, there's a trick in this. So these are formed during the weathering process, right? So there's aluminium and silicon floating around in solution, and given enough time and the right conditions, they precipitate as these quite complex and chemically attractive solids, I believe. But nature is never perfect, it's not pure, right? So sometimes where normally silicon would go into the structure, we find that aluminium goes in because it fits, right? And that happens sometimes in nature. And sometimes, well, these black dots are, we expect to find aluminium in the structure, but because of the mix of ions that's in that solution, the structure will form. Sometimes aluminium will be replaced during formation with something like magnesium. And in both cases, the replacing ion has got lower charge than what fits perfectly into the structure. And that means that many of these clay minerals actually are negatively charged. They have an electrostatic charge, and they're just sitting there in soils. And that's got to be balanced somehow. And it's balanced by cations which attach themselves to the external surfaces of the crystals. Now that's important. We'll come back to that in a minute. Now that process is what we call permanent charge. So remember, it's being formed as this crystal forms. So the charge deficit, if you like, is locked into the crystal. It can never change once that crystal is formed, unless we break it down somehow, which would be a fairly extreme process. And it's different for different types of clay. So kaolinite, which is a very common clay mineral in Western Australia, because of our highly weathered soils, they're actually not very electrostatically charged, but other types of clays are. So the smectites, things that we know, this is the kind of stuff we make kitty litter out of because it's very reactive, it absorbs smelly things. Bentonite and things, or montmorillonite, or illite clays and vermiculites that we use in potting mixes and things. You'd know them best from that. But they're natural minerals in soils. They're much more reactive because of this higher electrostatic charge. All right, so let's bear that in mind because that affects how these things behave. So we'll go on to talk about what else can happen. Now, electrostatic charge is quite an important concept with materials and soils. So the clay minerals, let's just quickly flick up to that structure again. Okay, so there's a structure there with central ions, aluminium and silicon, effectively metals if you like, and they're basically in this, if you can imagine having a box full of tennis balls, right? Shake them down and they will ultimately achieve a close packed arrangement with kind of tennis balls on the bottom layer and then the other ones sitting in the gaps in the layer. The structure of clays is kind of like that. You can imagine the oxygen atoms as being these tennis balls or ping pong balls or whatever, and in the gaps between those large balls are the small metal ions, right? Now that structure obviously has to finish somewhere. There's an edge to that crystal, right? And that edge, or the face of the crystal, because they're often quite flat, and the reason why they're called phyllosilicates is from Greek, phyllo meaning leaf, right? So they're kind of flat leaf or page-like materials. We often call them clay books because there's many of these layers stacked one on another. But they finish, right? So, and at the edge are these oxygen atoms. Now those oxygen atoms, remember we talked about acid-base properties on solids? Well, I mentioned that in passing. Well, here's the upshot of it. Those oxygen atoms behave as weak acids and bases. So you put them in a solution and they can dissociate or grab hydrogen ions from water. Now that ostensibly can change the pH, but the more important outcome for soils is that again it creates some sort of electrostatic charge on the surface. So at low pH, when there's lots of hydrogen ions around in the solution, those oxygen atoms will have an extra hydrogen ion on, if you like, so there'll be a positive charge. Right? Now that's a less likely outcome than this one here, because this, for clays at least, this neutral stage where there's no charge at all is around pH 4 or 5. Most soils have a pH above that, so mostly we're in this zone here of high pH where we've actually got a negative charge on those oxygen atoms at the surface. So we've got a negative charge in the clay already because it formed impure, while it was being born during weathering, but also it's got this surface charge which can change. Again, this is important in how they behave, and it's something that we need to understand. All right. Now, it's not just clays that do this. There are the hydrous oxide minerals, so the oxides of iron and aluminium and sometimes manganese have the same properties. They're oxides, right? So they've got a lot of their structure is oxygen atoms. That structure is not infinite. It finishes somewhere, and at the edge of the crystals, which may be very small, so there's a lot of edge, there are these reactive oxygen atoms. Right? So moving very fast, there's some of the types of minerals that we consider. Things like hematite, goethite, ferrihydrite, so alumina of different types, minerals like boehmite and gibbsite and so on. So what's the point of understanding this? Well, first of all, here's one mechanism where the pre-existing solids in soil can interact with ions. So that negative charge, which is almost always present on the little solid phases in the soil, has got to be balanced by something. Haven't got permanent electrostatic charge. You don't get sparks coming up from the soil each time you walk along, right? The charge is balanced, and it's balanced by cations in this kind of loose swarm, because electrostatic attraction is not a very strong process. Go away, please. Should have turned that off. And the point of this is that this is a very ecologically important place for elements to exist, because it, first of all, it's predominantly the major cations, and the major cations being the major rock-forming minerals, calcium, magnesium, rock-forming elements apart from iron and aluminium and oxygen. So they'd be, and silicon, they'd be things like potassium and sodium and calcium, magnesium, so ions which come from feldspars or micas or whatever, which also happen to be important plant macronutrients, right? So because soils are able to hold on to these elements in ionic form by that mechanism, and this ionic form is in very rapid equilibrium with the surrounding pore water, right? It's a reserve of plant elements. It stops essential nutrients escaping the soil, and it also means that if once a plant takes up calcium or magnesium or potassium from the solution out here, then the rapid equilibrium can readjust and release some more into the solution in plant available form. So cation exchange is a very important property of soils, and we need to understand that a bit. Right, I'm going to leave it there because it's coffee time. I have to see if you call me, tell them to go away, or just turn my phone off, and let's take a break for 10 minutes, right, and resume back here